All right. Here we go. Now we're cooking with gas. All right, Chemistry 1411. This is chapter 13. We're going to start with the first section, which deals with chemical equilibrium. If you go all the way back to General Chemistry 1, you saw lots of different reactions in that class, didn't you? For example, maybe a combustion reaction or a reaction like the one that's shown right here. And what's important here is that a lot of the reactions, in fact, most of the reactions that you looked at in general chemistry were irreversible reactions. That means you started with reactants and you ended up with just the products and you had no reactants left over. So if you take magnesium metal and you put it in sulfuric acid in a test tube, what you'll see is bubbles being formed, and that bubbles, or those bubbles, are hydrogen gas being released. And if you watch the reaction for long enough, eventually all the magnesium will disappear. It'll go away. And so that is an irreversible reaction, gives us only products. So the reaction just keeps going until there's basically a negligible amount of magnesium left, or maybe no magnesium left. But in this chapter, we're going to talk about something different. We're going to talk about reactions that reach what's called an equilibrium. So we're going to start with this however here. It says, however, many reactions stop short of completion. They don't just give us products. And they stop at a point where we end up with an appreciable amount of both reactants and products. So that means when the reaction is done, okay, there's no more change in concentration of reactants and products. We have some products and some reactants, and we call this chemical equilibrium. Now, this picture all goes together right here. You see we have time here on this stopwatch, or maybe clock, if you will. And you can see that time is equal to 0. All we have are hydrogen molecules. That's these guys here. And we have these iodine molecules, okay? But you can see that after a little bit of time, so maybe this is, I don't know, 16 minutes or something. After a little bit of time, you start to form some of these, right? Some of these HI molecules. But what else can we see? We still have the I2 molecules and we still have the H molecules. After a little more time progresses, if you were to tally up all of the H2, all of the I2, and all of the HI in this box here, what you would see is that the concentration, or the number of HI molecules, is increasing, and the number of H2 and I2 molecules is decreasing. And then eventually it gets to a point after a certain amount of time where we end up with a mixture of I2, H2, and HI, all their appreciable amounts, okay, but no more reaction is going to occur. So what am I saying? That no more H2 and I2 are going to disappear, and no more HI is going to appear. So we're not going to form any more products, and we're not going to consume any more reactants. Here's another example, okay? And again, when we talk about reactions that have an appreciable amount of the reverse and the forward reaction, we say that those are best represented as an equilibrium, right? Going back to general chemistry, again, this arrow here, this is an irreversible arrow, irreversible. This arrow here represents an equilibrium, equilibrium. Do not draw the arrow like this, like a single line with 2 points. That's something completely different. That's for resonance, which you would have learned in general chemistry 1. So again, a reaction with an appreciable reverse reaction in forward is often best represented as an equilibrium, just like we have shown here. So let's see what would happen. Let's say we had just some dinitrogen tetroxide, this molecule right here. That molecule is in fact a colorless compound, no color. Okay. Now, dinitrogen tetroxide can react to form nitrogen dioxide, which is in fact a brown compound. And what happens is, if you follow this sequence down here at the bottom, it says when dinitrogen tetroxide is put in a container, closed container at 100 degrees Celsius, what you're going to see is you're starting with just a colorless compound, but right away you start to see some brown color develop. Why is that? That's because the reaction is moving in the forward direction, isn't it? You're going from your colorless N2O4 to the brown NO2. Well, what's going to happen is that eventually you're going to build up enough of the NO2 that it's going to start reacting in the opposite direction, right? In the reverse direction to reform N2O4. So now we've got a forward reaction and a reverse reaction. Now, what I'm trying to get at here with you guys, and what I want you to understand before we really get into looking at problems is that at equilibrium, okay, the rate of the forward reaction is going to be equal to the rate of the reverse reaction, okay? So that would mean that the amounts or the concentrations of reactants and products is going to stop changing. Now, a picture is worth 1,000 words, and some students like to see everything in a graph, and there's nothing wrong with that. So this is just the same text, or no, sorry, this is a little bit different. But let's take a look at this reaction from the point of view of these graphs down here. Now, before we get into these bullet points, let's take a look at the graphs. The first one, the one on the left-hand side, is concentration plotted versus time. And the second one is reaction rate, right? Chapter 12, okay, rate versus time. Well, let's analyze these two graphs. If we think about the reaction rate first, okay, it says the rate of the forward reaction starts out fast, but it slows down as the concentration of N2O4 decreases. If you look at the rate of the reverse reaction, you can see that it's 0 when time is equal to 0 when you first start. But the rate of the forward reaction, it's got the steepest slope it's going to have at the very beginning. But what happens as time progresses, the rate of the forward reaction, you see that the slope lessens. So that means the rate decreases. And the rate of the forward reaction is increasing, right? Here we have 0. It's not progressing at all, where the rate of the forward reaction is 0. And then it's going to increase over time until they're both equal. So the rates of the forward and the reverse reactions are equal. And that is when equilibrium is established. If we think about what I just said in terms of concentration, and I find that for students, sometimes concentration's even, a simpler way to look at it. Look, if you're like, I don't follow you 100%, Mr. Dion, watch carefully. You start with just this. That's all you've got. You went to the store and you bought some N2O4. They were all out of NO2, okay? You just went to Safeway and you bought some. I'm kidding, okay? But anyhow, so that means when you start, all you have is N2O4. At time is equal to 0, you have none of this. 0. You have no NO2. What's going to happen is the reaction progresses, right? The concentration of the where's my highlighter? The concentration of the N2O4 is going to decrease. But look, it might be a knee-jerk reaction for you to say, well, it's going to decrease until there's none left. No, it decreases until it reaches a steady concentration. And conversely, the concentration of the NO2 is going to increase. It doesn't just go, indefinitely. It increases until it reaches a steady state. And when those concentrations remain unchanged, that's when you're at equilibrium. Now, I'm sure there's somebody out there who's saying, well, come on, Mr. Dion, if this is the concentration on the y-axis, the two concentrations aren't equal. No, they don't have to be equal. I didn't say anything about concentrations being equal. I said they remained constant. I didn't say they were equal. I said they were constant. So what we're going to see in this class is sometimes we'll look at reactions where you're going to have a big concentration of product. We'll look at other reactions where you won't have very much product, and mostly at equilibrium, you'll have the reactant. It depends on the situation, okay? All right, so there we go. So the amount of reactants and products are not ordinarily equal to each other, equilibrium. That's what I just told you, okay? It's not that the concentrations are equal. They're very rarely going to be equal. That would be a very specific case, okay? All that matters is that they remain what? They've got to remain constant. Give me a thumbs up when you just follow me on that idea. Just because the rate of forward reaction is equal to the rate of reverse reaction doesn't mean that the concentrations are the same. It just means the concentrations are constant. Okay, thanks, Mackenzie. I appreciate that. Good. That's, and if you're like, Mr. Dion, you're going so slow, speed up, man. No, I want to make sure you understand this concept, so much so that I'm going to bore you with even more details, okay? This is a picture from our textbook. You've got to understand that equilibrium is a dynamic process, right? Even though it appears as though nothing's happening, when the concentrations remain constant, there is still a forward reaction and a reverse reaction, but they're occurring at equal rates. Here's, this again is the example from our textbook. You have two jugglers. They're throwing I don't know what these are called, juggling pins. I don't know. Anyhow, I'm not a juggler, but the idea is that, there is a forward reaction and there is a reverse reaction, right? This guy's throwing them in this direction and this guy's throwing them in that direction. Okay.
Clubs.
But they're at a relatively equal rate, and so they're both normally holding roughly, it says here approximately, the same number of clubs. Sorry, juggling clubs, I guess. Anyhow, all right, there we go. You want even more? Here you go. Let me tell you. And equilibria is something you can see with a phase change as well. Now, this glass vial here, this is a sealed glass vial. This is called an ampoule, and there's different spellings of it. And in French, we spell it ampoule like that, but you could actually spell it like this too, an ampoule. I think that's correct. Anyhow, let me just spell it the way I know. So an ampoule, it's just a sealed glass vial. Now, does anybody know what the two liquids are in the periodic table? There are two elements that exist as liquids at room temperature. Could anybody tell me?
Mercury and gallium?
No, gallium is actually a liquid or a solid at room temperature. It's got a really low melting point. You're absolutely right. The gallium has a very low, right? You see pictures of people melting gallium in their hands. The two elements that are liquids at room temperature are bromine and mercury. Yeah, you guys are good students. Anyhow, that's great. So look, if you take bromine, so this is, let me use a different color pen here, I guess. This is bromine in the liquid phase here, Br2. And this is Br2, and this is bromine in the gaseous phase. So if you take some bromine in the liquid phase, which again, it's liquid at room temperature, and you put it in a sealed glass vial, what you'll see is that immediately you'll start to see some of it vaporize, and then it reaches an equilibrium where the rate of evaporation is equal to the rate of condensation, right? So we can even write that on the top, that's evaporation, and on the top, that's condensation. Anyhow, I just want you to know, I just want to give you some examples of equilibria. All right. Anyhow, there you go. All right. Well, let's move on to section 13.2 and talk about equilibrium constants. Equilibrium constants, and this is going to come up almost Avogadro's number of times in this chapter. Okay, so first let's discuss what's called a reaction quotient. So a reaction quotient is a new variable, and we're going to use the letter Q, capital Q, to represent a reaction quotient, and it allows us to provide a mathematical expression for the amount of reactants and products at any point in a reversible reaction. So by at any point, it means not necessarily at equilibrium. Okay, an equilibrium constant is something else. So let's say we have a general reaction like this one here. You have A times the stoichiometric coefficient M, B times the stoichiometric coefficient N is in equilibrium with C and D to the stoichiometric coefficients X and Y respectively. Well, first of all, if A, B, C, and D are either gases or aqueous solutions, meaning if they are in the gas phase or aqueous phase, and X, Y, M, and N are all the coefficients, then to write an expression for the reaction quotient, you would use this formula right here. Reaction quotient is equal to the products of the product, the concentration of the products to their stoichiometric coefficients divided by the concentration or the product of the concentration of the reactants to their stoichiometric coefficient. So this is a formula that you need to have memorized. And if you do the practice problems, you're going to use this formula so many times that you will become very accustomed to using the formula. So QC, and there we go. So that's our reaction quotient. Now, again, keep in mind that this is not necessarily equilibrium. We can use it to represent the amount of reactants and products at any time in a reversible reaction. And if you read the textbook, you've learned about equilibrium constant, and we're going to learn about the comparison of equilibrium constant and reaction quotient. So let's talk more about reaction quotient. If we're dealing with concentrations, they have to be expressed in molarity, which is the number of moles per liter. The product concentrations are in the numerator, went over that already. The reactant concentrations are in the denominator, and each concentration is raised to the power of its coefficient from the balanced equation. So you can see that learning how to balance equations in General Chemistry 1 was not in vain. They come up all the time in in general chemistry too. All right, a little more information before we get into some problems here. Let's take a look at some more information here. It says the numeric value of the reaction quotient for a given reaction can vary prior to equilibrium. All that means, that's just a politically correct way of saying, you know, the reaction quotient, it doesn't have anything to do with equilibrium, right? It might be the same as what it is at equilibrium, or it might be expressed at equilibrium, sorry, but it doesn't, it's usually not used for equilibrium. Now, if you understand math, you'll know that the value of this is going to depend on the concentration of products in reactants, right, at the particular moment. So that means that QC is going to vary with concentration. And we, as long as we have the concentrations of our reactants and products, we can calculate QC at any point in a reaction. So if you're saying, hey, Mr. Dion, if I have a reaction and I measure, the QC at different times, if the concentrations are changing, that means my QC can change. Absolutely. Okay, you can literally have an infinite number of QCs for a reaction. However, oftentimes we're going to calculate QC at the start of the reaction using the initial concentrations. Okay, you're going to see that come up over and over in this class. Now, I told you a couple of slides ago, right here, I said that not only could you evaluate QC using aqueous species, you could also do it for gases. So how does QC relate to pressure? Okay, that would be a very good question. And instead of QC, the subscript C, if you have QC, the C stands for concentration. When we're given pressures, we can calculate QP, which stands for pressure. Okay, and we can use partial pressures, and the pressures are usually in atmospheres in this class. Okay, so there we go. So QP and QC, and we're going to look at examples where we solve for QP and QC. Again, when we're at equilibrium, we have a different variable that we use, and we call that capital K, and that is the equilibrium constant. Okay, and this is something else that we're going to look at, constantly, no pun intended, in this class. I usually say Kc for the equilibrium constant when we're using concentrations, and then Kp when we're dealing with pressures, okay? But the main idea is that it's capital K for the equilibrium constant. Do not confuse this with lowercase k, right? That was chapter 12. Okay, that was a rate constant. All right, so again, to define, when we have a reaction quotient at equilibrium, when the concentrations of reactants and products remain constant, that's called the equilibrium constant, and we use the exact same formula that we saw a couple of slides ago. Okay, exact same formula. So QC is not necessarily at equilibrium, but if it is, it's called the equilibrium constant, Kc, and we use the same formula that we would for QC. All right, let's talk about a little bit more background before we get into some problems. I have a couple more slides, and then I promise we're going to look at some problems. The value of that equilibrium constant is independent of the amounts of starting reactants and products. The rate of the equilibrium constant is dependent, the value of the equilibrium constant is dependent on temperature. So what does that mean? That K, okay, depends, or maybe we'll do it like this. We'll say K varies with T. So if we change the temperature, we're going to change the equilibrium constant. This is something that for some students is very intuitive, but for others it's more complex. And I have a couple slides to explain this. But the value of K, big K, is going to not depend on the concentrations of the starting reactants or products. The reaction is always going to do what it has to do to establish the equilibrium constant. And we will look at several examples of that. But the magnitude of the equilibrium constant, the size of it, tells you how much the reaction has progressed. And that should make sense because, the numerator are the products, and the denominator represents the reactants. So that tells me, I'm just going to ask you guys, if my Kc is a gigantic number, would I have mostly products or mostly reactants if I had a really big Kc? When I'm at equilibrium, would I be mostly products or mostly reactants with a large Kc?
Be mostly products.
Absolutely, right? Because that would mean your numerator would be a really big number, right? Okay, great. I'm really happy that you all answered the right thing, okay? Conversely, if the reaction was at equilibrium and was mostly reactants, then your Kc would be a really small number, right? Because you'd have a big number in your denominator, right? Just some simple math. But again, sometimes it just takes a little while for us to wrap our head around that. Well, this is just a summary here, okay? And I'll skip over a lot of the details here because we've discussed it. But if K is much, much greater than 1, we can say that usually the equilibrium is going to favor the products. If it's way less than 1, then it's usually going to favor the reactants. And if it's around 1, then we could say, it's not going to favor either, okay? Now, this is just a quick aside. And our textbook goes into some detail about this. Note that the size of K, so your equilibrium constant, and the time that it takes to reach the equilibrium, they have nothing to do with each other, okay? You can have a reaction that is has a large K, it's mostly products at equilibrium, but it's really slow, okay? They are not directly related to each other, okay? Anyhow, and we discussed that in chapter 12, so I'm not going to spend any more time going over chapter 12. Suffice to say that the size of K, if you're like, well, what the hell does the magnitude of K depend on? Okay, it depends on thermodynamic factors like enthalpy and these two factors here, which we will discuss later on in this class when we discuss thermodynamics. Some of you probably know entropy and Gibbs free energy, but if you don't stress about it because we will cover them when we need to, which will be later on, not for another month or two. All right. I'm going to skip this slide and get right to some problems here. There's not a whole lot of new information here. I guess we could take a look at it. Anyhow, it says here, if you have this reaction and you were to write an equilibrium constant, I'm just kind of rehashing the same thing over and over here. It would look like this, B over A. So if you had an initial concentration of A that is 1 and B that is 0, then you'd have 0 over 1, and 0 divided by 1 is 0. So if you take your calculator and you take 0 divided by 1, you end up with 0. And so the equilibrium is, it's going to proceed to the right. So it's going to go towards the products. If you have only products, so if you only have B, then it's going to proceed toward the reactants. Anyhow, with all that in mind, let's look at some problems here. I think I've talked a long time. Who likes doing practice problems in class? Just me? All right. I'm assuming everybody does because it's the best way to master the content. And let's take a look at a practice problem here. First one's not meant to be anything, mind-boggling. Just says write the equilibrium constant expression for this beautiful reaction right here. What I notice right away is that everything is aqueous. So that means that everything is going to be included in the equilibrium expression. So we'll write that K is equal to the concentration of iron 2 plus to the power of 2 times the concentration of I3 minus to the power of 1. We'll leave the 1 out. Divided by the concentration of iron 3 plus to the power of 2 multiplied by I minus to the power of 3, like that. Okay, there we go. Now that you've seen it done, you could try writing one for this reaction right here. And B, same thing. We would say K. You can see that everything is gaseous, right? We can measure the concentration of a gas. So we could say the concentration of carbon disulfide to the power of 1 times hydrogen to the power of 4 divided by methane to the power of 1 times H2S, hydrogen sulfide to the power of 2. Give me a thumbs up if you like. Mr. Dion, I can write an equilibrium expression if you give me a nice balanced equation. So Autumn asked a question. She says, what if you have a balanced equation that contains solids or liquids? Okay, Do we disregard those? The answer is yes, we do. In Autumn, I have a whole slide dealing with those kind of situations. That's called heterogeneous equilibrium, where we have more than one phase in the reaction. We will discuss that in detail, okay? I will not leave you hanging and, waiting, like what the heck's going to happen, Anyhow, I didn't leave myself a lot of space here, did I? So let me take a look at this problem here. It says 1 mole of each nitrogen and hydrogen were in a sealed 1 liter vessel at 500 degrees Celsius and allowed to reach chemical equilibrium. At equilibrium, the concentrations of nitrogen and hydrogen were 0.921 and 0.763 molar, and the concentration of ammonia was 0.157. What's the equilibrium constant? Well, we don't have a balanced equation, but I didn't read the whole question, and it tells you to write, it asks us to write a chemical equation for the formation of 1 mole of ammonia gas from its elements. So how would we do that? Well, if we're going to form 1 mole of ammonia, that's NH3 in the gaseous phase, okay, and if it's at equilibrium, what elements do we need to combine to form ammonia? Well, ammonia is made from nitrogen and hydrogen. Nitrogen is a diatomic element, it's N2 gas, and hydrogen is a diatomic element, it's H2 gas. But this is not balanced. Now, if the stoichiometric coefficient of the ammonia needs to be a 1, what would I multiply N2 by to make 1 atom of nitrogen? And the answer is I'd multiply it by a half. And then for my hydrogen, okay, what would I multiply that by? H2 to get 3. Well, the answer is 3 over 2, right? 3 over 2 is 1.5. 1.5 times 2 gives you 3. So you should be able to come up with this expression right here. Now that we have the expression, we can write our K equilibrium, right? We can say that K for that reaction that I have highlighted in yellow is equal to the concentration of ammonia divided by the concentration of nitrogen to the power of a half, or a square root, times the concentration of hydrogen to the power of 3 over 2, like that. Now we can just plug in all the concentrations because they were given to us. And let's do that. So this is A. We're going to plug in those concentrations. So I have 0.157 divided by, notice I'm leaving the molar out, and I'll explain that in a second, divided by 0.921 to the power of a half, times 0.763 to the power of 3 over 2, or 1.5. Okay? Now, you noticed that I left the units of concentration out. All right? The reason we leave those out is because they're not important for our equilibrium constant. The book gives you a little bit more detail on it, okay? And it says, sometimes they are relevant, but that would be beyond the scope of our class. So whenever we calculate equilibrium constants, we're gonna leave the concentration out. Okay? So just hear ye. We're always gonna leave concentration out. Well, you've got to know how to use your calculator and take 0.157 divided by 0.921 to the power of a half times 0.763 to the power of 3 over 2. And when we do that, we get that our K, and I'm going to call this Kc. Why? Because they're concentrations, right? They're not pressures. Kc is equal to, and I've already done this one, it's equal to 0.245, just like that. So there's our Kc. Now, in the next problem, or part B, it says 1 mole of ammonia was sealed in a 1 liter vessel at 500 degrees Celsius and was allowed to reach chemical equilibrium. At equilibrium, here are the concentrations. They're all given to you. Calculate the equilibrium constant for this reaction. Let's do the exact same thing. And there we go. Let's give it a try. Our Kc, concentration, is still equal to concentration of ammonia divided by, okay, so we have that expression. We have our new concentrations. We have 0.203 divided by, I can't read my own writing, 0.399, is that what it is? Yep, 0.399 to the power of a half And then 1.197 to the power of 3 over 2. That. Okay, there we go. Now, before I answer this problem and type the answer in, I want you to notice something very important here. If we read question A, it says blah, 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 at equilibrium. Here are the concentrations. Look in B, same thing. It says 1 mole of ammonia, blah, 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 was allowed to reach chemical equilibrium. They're both reactions are done at 500 degrees Celsius. Okay, they're both done at the exact same temperature. Do I even need to punch this crap in my calculator? No, not if I did this one correctly. The Kc should be the exact same because equilibrium constant is not going to change with a change into as long as the temperature remains constant. So when you punch all that in, you're going to find that you end up with 0.245. You can see I'm getting very excited about this, okay? It's because I just want you to understand that the concentrations, and I'll write it down here, the concentrations, okay, will always adjust so that K is satisfied. And this means at equilibrium, of course. Okay, so there's literally an infinite number of different concentrations that we could have that will satisfy the equilibrium constant. If you are confused about what I'm saying, let me explain it to you in the simplest possible way I can. If I was to ask somebody on the street, what divided by what equals 2? Give me two numbers. Somebody might say 2 over 1. Somebody might say 4 over 2. Somebody might say 16 over 8. Right? Somebody might say 14 over 7. The answer is there's an infinite number of combinations of x over y that can equal 2. There's literally infinity answers. The same thing applies here. There are infinity number of different, concentrations that are going to equal the Kc. The idea is this, is that even if you, and you're like, well, come on, Mr. Dion, what if I just started with only the nitrogen and hydrogen and didn't have any of the ammonia? The idea is this, and pay very close attention to, read my lips, okay? The reaction, when it establishes equilibrium, it's going to satisfy the equilibrium constant as long as the temperature remains the same, right? Give me a thumbs up if you're like, hey, Mr. Dion, I think I follow you on this concept of equilibrium constant, but I want to solve more problems. All right. Sierra, what you could do is you could go back and try this problem, okay? And you could multiply everything by 2, for example, and give it a shot and see what you get for a Kc. All right, well, let's move on and try some more problems. I think that on, what's today? Is today Wednesday? I think that on Friday, I'm going to rearrange my slides maybe and give myself a little more room to solve these problems. I'm making myself nervous, but anyhow, not a lot of room on here. But let's try some more practice. Imagine you're on exam number 2 and you're like, Mr. Dion, I just finished exam 1. Can't you get me some slack? No? Okay. Let's take a look at question 3. It says a mixture of ammonia, nitrogen, and hydrogen was sealed in a 1-liter vessel at 500 degrees Celsius. Allowed to reach chemical equilibrium. Good. At equilibrium, the concentrations of nitrogen and hydrogen were this 0.259 and 2.59 and 2.77 molar. Calculate the equilibrium concentration of ammonia for this system. Okay. Hint: we'll use the information from the previous question. So I'm going to use the same expression for the equilibrium constant that I did from the previous question. I'll write it down here if you don't follow me. So what I mean is I'm going to use the 1/2 N2 plus 3 over 2 H2, right, is in equilibrium with NH3. So we know that our K concentration, so I'll write Kc, is equal to concentration of NH2. This is the third time I've written this down today, isn't it? H2, sorry, keep it in order. N2 to the power of 1/2 times H2 to the power of 3 over 2, like that. And we know that it's equal to, we know that Kc is equal to 0.245. So we have all that information. So in this problem, we have Kc, we have the concentration of our nitrogen, and we have the concentration of our hydrogen, and we're going to solve for the concentration of ammonia. So if we plug some numbers in there, we get that, and I'm just going up here, we have that 0.245 is equal to the concentration of ammonia, which is what we're looking for, divided by 2.59 to the power of a half times 2.77 to the power of 3 over 2. When you solve for the concentration of ammonia, and I'm not going to go through all that, you would just take 0.245 and multiply it by the denominator. And you end up with the concentration of ammonia being something. Let's see here. What is it? 1.82 molar. All right, there we go. Again, I'm going to write this down here. There are an infinite number of concentrations that will satisfy K. Okay? All right. Camden, I agree. Repetition does create muscle memory. There's no doubt about it. All right. Now, I didn't leave myself a lot of room for this one. Again, next class, I'm gonna work on this because question number 4 is a really important question. Did anybody solve this one before class? Not all at once. Okay. Maybe nobody did. Maybe somebody did. Anyhow, let's take a look at it. Let me ask you a different question, since maybe nobody did the problem. Has anybody here heard of an ice table before? An ice table?
Yes.
I don't mean a table made out of ice. Okay, good. So ice table, ice stands for initial, change, and equilibrium. Okay, so if you've never heard of an ice table, don't worry about it, because I'm going to teach you what an ice table is in this problem. I made a note for myself. I said, introduce the concept of an ice table to your students here. So let me show you what an ice table is. And trust me, you're going to use ice tables, Avogadro's number of times to solve all kinds of problems in this class. Okay, let's read the question. It says 1.00 mole of pure HI is introduced into a 1 liter reaction vessel and are allowed to reach equilibrium according to the following reaction. Here's the beautiful reaction right here. They give you a balanced equation, so don't have to worry about that. At equilibrium, 0.800 moles of HI remains. The temperature remains constant. Calculate the value of Kc. Well, we know from this equation right here that our Kc is going to be equal to the concentration of H2 multiplied by the concentration of I2 divided by the concentration of HI squared, like that. But we don't have the concentration of any of these, do we? All it tells you is at the beginning you put in 1 mole of HI, and at the end you have this much HI remaining. Well, let's use the balanced equation to help us solve this problem. So I'm going to rewrite the balanced equation. 2HI, maybe I'll move it over a bit. 2HI is in equilibrium with H2 plus I2. So initially, we start out with 1.00 moles per liter of HI, right? Because we have 1 mole in 1 liter. Now, you can do that math in your head, can't you? 1 mole per liter, that's the same thing as saying, and I'm just going to spruce it up here, 1.00 molar, right? That's your initial concentration of HI. But remember, you don't have any H2 and I2, right? All you went to the store is you went and you bought some HI. So that means you've got 0 molar H2 and you've got 0 molar I2. Well, what's going to happen is you're going to end up with some kind of change. And it tells you that at equilibrium, you've got 0.800 moles of HI left over. You've got 0.800 moles of HI in 1 liter. Again, that's just math we can do in our head, so I'll erase that. 0.800 divided by 1 is 0.800 molar. So that's how much HI, you've got an equilibrium. And you're like, okay, cool. Now I've got this, but I'm missing these two. How am I going to figure those out? Let me show you. We used the ICE table and some algebra. Look at the stoichiometric coefficients. For every 2 moles of HI, you have 1 mole of I2 and 1 mole of H2. So that means, and we're going to use some variables here, when we go from the 1 molar to the 0.8 molar, we're going to put in, and we're going to say, well, we're losing 2x, right? Because the concentration is decreasing. And we know that if we're losing 2x, right, for every molecule of HI, since there's twice as many molecules of HI as there are of H2 and I2 in our balanced equation, that means we're going to be gaining x for H2 and we're going to be gaining x over here. Again, if you're like, what? Where are you getting these x's from, man? All I'm saying is I'm throwing this in here as a variable, right? Because the concentration is decreasing. 0.8 is less than 1, so that's why I use a negative sign. Where does the 2 come from? It comes from the stoichiometric coefficient, because I'm going to lose twice as much HI as I would gain H2 and I2. Okay, just the stoichiometry. So if I lose 2x, that means I'm going to gain 1x here, and I'm going to gain 1x here. Again, that's based on the stoichiometric coefficients. I've said it like 3 times, but I want to make sure you follow me. So if you have 0 plus x, what does that give you? That means that at equilibrium, you're going to have an x concentration of H2, and you're going to have an x concentration of I2, like that. Well, what is x? Well, we can just do some quick algebra, right? If we go from 1 to 0.8, that means that we ended up losing 0.200 molar is equal to 2x. That means the x is going to be equal to 0.100 molar. Now we can rewrite this, and we can say that at equilibrium, and I'll just rewrite it again, we have 0.800 molar of HI, and since x is 0.1, we already solved for it. We have 0.100 molar here and 0.100 molar over there. Now we have everything that we need. We have the concentration of the product, or sorry, the reactant and the 2 products in order to solve for Kc. Now it's just a matter of plugging the numbers in. So we're going to say that Kc is equal to 0.1 times 0.1, which is the same thing as 0.100 squared. Remember, we leave units out. Equilibrium constant is a unitless number divided by 0.800 squared. Now it's just a matter of plugging the numbers into your calculator, and we get the Kc is equal to 1.56 times 10 to the negative 2, just like that. And so that is how we use what is called an ICE table. If you're like, Mr. Dion, I'm not 100% sure about this ICE table. Well, I can promise you, and I don't promise anything to anybody. I told my wife on our wedding day, it's a 3-year commitment. I promise you that you're going to see enough ICE tables that you will more than likely get the hang of it, okay, if you stick with it, all right? We use ICE tables literally, well, not literally, but almost Avogadro's number of times in this class. Give me a thumbs up if you're like, hey, Mr. Dion, I'm even part of the way with me on the ICE table. You don't have to be 100%. I don't expect you to learn everything the first time you see it. Nobody could do that, okay? It's going to take some time with you alone, calculator, practice problems, pencil, paper, maybe a glass of water, I don't know, and just sit down and give her, so to speak. All right, well, let's try another problem here. This is question 5. You can see you had to listen to me ramble on a little bit today, but I am rewarding us with some fun problems. So here's another good one. It says a flask, and this is question 5, a flask contains 1 molar each of nitrogen, hydrogen, and ammonia at 500 degrees Celsius. It's like, jeepers, that same old reaction keeps showing up in this class. Calculate Q. Oh, yeah, we got 1 mole of each. Yep, 1 molar of each. It says calculate Q for the system and say whether the system is at equilibrium or not, and then tell me which direction the reaction is going to proceed to reach equilibrium, right? This question is just one of those classic questions that I'm going to ask you. You know, the reason we're doing this is just to solidify, right? Just to understand what the hell is going on. So let's do it. Pardon my language. Look, we've got our beautiful balanced equation. Somebody asked me a question earlier, you know, about this. Can we use it, with different stoichiometric coefficients as long as it's balanced? The answer is yes. So let's write out our expression for QC. QC, a reaction quotient, is going to be equal to the concentration of ammonia to the power of 2 divided by nitrogen. There we go. To H2 to the power of 3. There we go. So we have everything. The concentration of everything in this whole reaction is 1. So let me get this out here. Is equal to 1.00 squared. Again, I'm leaving the units out because Q and K are unitless. Divided by 1.00 times 1.00 cubed. I think that everybody can solve this in their head. You don't need a calculator for this. You get that QC is equal to 1.00. What do we see? We see that we already calculated Q, so this is part A. What do you see for part B? QC is a lot greater than KC. So if QC is greater, that means that you have more products than you would than reactants, or sorry, you have an excess of products, right? So in order for the reaction to reach equilibrium, could anybody tell me which direction the reaction would have to shift, to the left or to the right, if I have too much products or an excess of products?
Towards the reactants. To the left.
It's going to shift towards the reactants, right? Shift to the left, okay? So since QC is greater than KC, we'll say, therefore, shift to the left or reverse, or somebody unmuted their mic and said reactants. That's fine too, okay? As long as you understand the concept. I am really happy, you guys. You put me in a good mood. My students are giving me really good answers to these problems. And I hope that you're thinking like, hey, this isn't that bad. It's not that bad, okay? It will get more complex, but the idea is, we want to figure out what the heck is going on and see if we can understand the first few concepts we look at. Look, you can see how this would be a great question for a multiple choice exam. I have let me rewrite it here. Scenario where Q is greater than K, we'll call that A. If we have a scenario where Q is less than K, we'll call that B. And if we have a scenario where Q is equal to K, we'll call that C. I'm pretty sure that most of you could answer this, pretty quickly, but let's just go over it. If Q is greater than K, just like we saw here, the reaction is going to have to shift towards the reactants. So I was just thinking, an easier way to say it, why don't we put concentration of product is going to have to drop. Okay, will drop. Maybe I'll put will drop. Will drop. And we'll put concentration of reactant will increase. Let's do it like that, okay? Then if we have the scenario where it's the opposite, come on, there we go. So if we have the opposite scenario, in that case, it's going to change, right? It's going to be the opposite. So if your Q is lower than your K, then the concentration of the product is going to increase because you want to have a bigger denominator, and the concentration of the product will drop. And then if QC or Q is equal to K, then system, we'll put here system is at equilibrium. Equilibrium. All right. Good. Great. I'm pumped. Well, when I was putting together my slides, I said, I'll kind of get to this question. And, I'm middle-aged. I've earned the right to repeat myself like an old man. And you're going to hear me repeat myself again here, okay? Now, this slide is based off of a figure that's in your textbook. It's figure 13.6 in the OpenStax book. I just thought it was so well presented that I want to rehash it again, okay? So I'm explaining the same thing for, I don't know, maybe the third or fourth time here, but I want to make sure you follow me before we move on, okay? I want you to, as many students with me as possible. Let's take this reaction here. You have carbon monoxide plus water is in equilibrium with carbon dioxide and hydrogen. Beautiful reaction. We have an equilibrium constant. It's 0.640, great, okay? and it's at a temperature of 800 degrees Celsius. Wonderful, wonderful. Now, again, I've told you this many times, there's many ways to reach the KC, okay? You could start, oops, what am I doing here? You could start with just the reactants, okay? You could start with just that. You can start with just the products, that can happen. And you can start with, a third scenario. You could start with a mixture of a little bit of everything, okay? The bottom line is this, is that the reaction is going to do what it's got to do to achieve equilibrium, okay? Another way of saying that is what's down here at the bottom. The value of K, the equilibrium constant, is independent of what you're starting with. Trust me, the reaction, nature is, like I worked in industry for 15 years as a bench chemist. And, the first job I ever had, I was 24. I was getting really frustrated at this reaction that wouldn't do what I wanted it to do. I kept trying it and it would fail. I tried again, it failed. I tried it again, it failed. And I worked with a guy who had, 30 years experience in the lab. I was so frustrated, I was probably swearing at it or something. And finally, he came up to me, just tapped me on the shoulder, and he said, molecules and atoms are going to do what they're supposed to do, man. Okay? They're going to do what they're supposed to do. They're not disobeying you just because it's you. Okay? They're going to do what they're supposed to do. So that's another way of me saying they're going to adjust to reach equilibrium, to satisfy that equilibrium constant. Here's the picture, depicting these three scenarios here. Okay? It's color coded. So let me rewrite the reaction here. You have CO, gaseous plus H2O. I could have put this on here, couldn't I? Gives you CO2 plus H2. Okay, so there's our reaction. We know that our QC would be calculated concentration of CO2 multiplied by the concentration of H2 divided by the concentration of carbon monoxide times the concentration of water. Okay, there's all the players. Now here are the scenarios. Look, over here, we're starting with 0.0243 molar of each carbon monoxide and water. So only reactants, okay? We got reactants only here. So the Q is equal to 0, right? Because you've only got reactants, so you've got something, you've got 0 divided by something, right? 0 divided by something gives you 0. Then here's another scenario where you have 0.0468 each of the two products. So that means you've got something divided by 0. Anything divided by 0 gives you infinity. So you have the two extremes of the Q. And if you're wondering, Mr. Dion, where are they getting these numbers from? They're just random. I don't know. The person who wrote the textbook picked them. I don't know. They picked them out of a hat. It doesn't matter. Okay. And then here you have a scenario where the Q is less than the K, because the K was 0.64, right? We know that KC is equal to 0.640. That was on the last slide. Anyhow, if you're like, Mr. Dion, I'm not following you. Look, I'll say it for the last time, then I promise I'll leave you alone, okay? Well, look, it doesn't matter what you start with. All three of these different reaction scenarios of these mixtures, they're all going to adjust themselves so that if you plug in these numbers, or these numbers, and you plug them into this formula, you're going to end up with K every time, okay? Again, I know I've repeated this a lot, but I think it bears repeating when we first start out on this chapter. Give me a thumbs up if you just follow me on the concept. So Stephen says, what if one reactant is far greater than the other reactant? So you're saying, like, what if this was, 0.5 and what if this was 0.1? The answer is it's still going to adjust to satisfy. Okay, it's still going to do it. All right, there are no exceptions. Cool? All right. And Stephen, it was Stephen, right? Yeah, Stephen Dillahunt. Trust me, we'll look at every scenario. By the time we get to the end, you'll be like, I've seen everything now, right? Okay, well, let's talk about some more rules here. And this is getting back to what Autumn asked me about earlier. She said, what if you have solids and liquids, Mr. Dion? We're going to talk about that in a second. But so far, we've only talked about scenarios really where we had all the reactants and products in the same phase. So either all are aqueous or all are in the gaseous phase. Again, that's the most common. Oh, yeah, aqueous phase or gaseous phase. It shouldn't say liquid phase. It should say aqueous phase there. Sorry, that's a typo. I should change that. Sorry about that. Anyhow, reaction quotients include the concentration or pressure terms only for gaseous, okay, and solute, okay? So if you look at, come on, get out of there. If you look at this reaction here, you see everything is aqueous. And so all three of the players end up in the equilibrium constant expression. But if you look at the second one, okay, you have water, which is a pure liquid. It's not going to end up in the equilibrium expression. You see that it's not in the denominator. It's not there. And why? Because a liquid is a pure substance. Okay, it's not a solution. Okay, you can't measure the concentration of pure water, pure anything. Okay, so we leave that out. And then for the last one, exact same thing applies here. You have a gas, and you can measure the concentration of a gas, just the number of moles per volume. So there you go. Okay, homogeneous equilibrium. And as far as heterogeneous equilibrium, I mean, it's 10:30 right now. I don't know if we'll get there. We won't get there today. I don't want to go too fast. So here we go. Let's talk about KC and KP. You probably noticed that at the beginning, I mentioned KP to you, right? I said, and then every problem that we've dealt with up till now dealt with KC. And you're like, when are you going to talk about KP, Mr. D? And you mentioned it. You said we could derive an expression for it. Okay, but we're going to talk about it a little bit more right now. And what specifically I want to talk about is the relationship between KC and KP. Because you might be wondering, does KC equal KP? Are they the same? And the answer is it depends. And you're like, I'm so sick of it depends in chemistry class, but it does depend. And I'm going to explain when they will be the same. And trust me, it's not a mind-boggling situation. So let's look at this slide here. It says for gas phase solutions, the equilibrium constant can be expressed in terms of concentration or partial pressures, either one. So you can use Kc or Kp. But what would the relationship be between Kc and Kp? Well, you got to go back to ideal gases, right? You guys remember this chestnut over here? PV equals nRT. I know you all have that memorized from General Chemistry 1. Well, could we derive an equation that relates pressure in concentration? And the answer is yeah. Yeah, absolutely we can. Okay. If we take PV equals nRT and we solve for P, we can factor out the N over V. And we know that concentration, right, which is in moles per liter, is the same thing as the number of moles divided by the volume. So this is concentration right here, right? This is molarity. So we can derive this expression P is equal to mRT. I'll just throw this out here. Every once in a while, and this has got nothing to do with, it does have something to do with it, but I'm not going to bring it up the rest of the class. But sometimes if you Google this equation, you'll see P is equal to CRT, and the C just means concentration. Okay, so if you're the kind of person who has to, second guess everything I say and look it up on YouTube or Google, by all means, go ahead and do that, But sometimes we use C. It's like, do you guys remember from Gen Chem 1, sometimes you'd see C1, V1 is equal to C2, V2, and then you'd Google it, you'd look it up on YouTube, and somebody would say M1, V1 is equal to M2, V2. They're the exact same thing, okay? Anyhow, you're probably like, I get it. Anyhow, so here's the relationship between Kc and Kp. This is a formula you're going to have to know. It's that Kp is equal to Kc multiplied by RT. R is the gas constant, shown right here, 0.08206 liter atmospheres per mole Kelvin, okay, to the power of delta N. Now, you might be wondering, where does this equation come from? And let me show you. And the book goes through it in detail, but I wanted to actually write it down. I didn't want to just copy and paste it into a slide. So see if you can follow me here. I'm not going to ask you to derive this, but I like my students to understand, like, where the hell do some of these formulas come from? If we have this equation, okay, if we have A plus B, and I have our stoichiometric coefficients here, is in equilibrium with C plus D, like that. Let's say that everything is measured in pressure, okay? Everything is measured in atmospheres. Then we could derive an expression for Kp, couldn't we? Okay? we would say, and I went over this earlier with you, but we'd say the pressure of C to the power of little c times the pressure of D to the power of the stoichiometric coefficient divided by the pressure of A to the power of lowercase a times the pressure of B to the power of lowercase b. Okay? Not a stretch there. I think everybody could derive the equilibrium constant using pressure. No problem. Okay. Well, what did we also see on the last slide? And I'll write it over here in red. We saw that pressure is equal to molarity times RT. Now watch. If these are all pressures, right, why couldn't I write them out as molarity, which is concentration, right, times RT? I can. So watch. If I was to write this out as a KP again, and we'll probably run out of room, but I'll try my best, I would say that KP is equal to the concentration of C times RT to the power of C times the concentration of D times RT to the power of little d. There, I got just enough room, times the concentration of A times RT to the power of A times the concentration of B times RT to the power of little b, like that. Now it's just a matter of using a little bit of algebra. So now we can rearrange this formula, and we can say that Kp is equal to the concentration of C to the power of C times D to the power of little d times RT to C plus D, right? And I'm just doing the algebra here. I just factored out this part here. Since I'm multiplying them, I add the exponents. And then I plug in my denominator. Concentration of A to the power of little a times concentration of B to the power of little b times RT to the power of A plus B, like that. Anybody recognize this chestnut right here? That's Kc, isn't it? So now we can say that Kp is equal to Kc times RT to the power of C plus D subtract A plus B. Okay? In C plus D, right, subtract A plus B, that's our delta N. Okay? So we'll write out that Kp is equal to Kc times RT to the power of Kc times to the delta N. And again, the delta N is just equal to the number of moles of gas, the final number, subtract the initial number of moles, total moles of gas. Okay? So that's where you get the expression from. Again, I'm never going to ask you to derive that. But you know what? I remember learning this formula when I was a student in general chemistry back in 1994 or something like that, 95. And I remember seeing that and be like, where the heck does that come from? And I just had to know. And so, you know, it's in every general chemistry textbook. And there we go. All right. So Autumn is asking a question. Why is N the only portion being divided by P? So N is not being divided by P. I'm not 100% sure what you mean. So maybe you could shoot me an email about that one. All right. Well, do we have time to do another problem? I think we do. And this problem involves the equation that we just looked at. Okay. Our good old friend, Kp is equal to Kc times RT times delta N, like that. All right, it says use the value of Kc for the formation of 1 mole ammonia from its elements at 500 degrees Celsius. Mr. Dion's addicted to this reaction, isn't he? To calculate the value of Kp for this reaction at the same temperature. All right, so let's do it. I don't know if we have enough time, but I'll go for it as fast as I can. We have 3.5 moles of H2 plus 1/2 moles of N2 gas, okay, is in equilibrium with NH3 gas, like that. NH, that's supposed to be a number 3. See what happens when you try to rush. Okay, you do stuff like that. Okay, what's our delta N? Delta N is equal to the total number of moles of gas over here, which is 1 subtract the total number of moles of gas over here. 3 over 2 plus 1 over 2. That equals 4 over 2. That equals 2. So 1 minus 2 is equal to negative fun. There we go. So then we're going to write out that our Kp is equal to our Kc, which was 0.245 multiplied by 0.08206. I'm going to leave the units out in the interest of time. We don't need them anyway. Multiplied by our temperature, which is 500 degrees Celsius, which is 773 Kelvin. So 773, like that. All of that, only this part is to the power of -1. And when you punch all that spinach into your calculator, you get your Kp is equal to 3.86 times 10 to the -5, like that. Now, you probably realize, and I'll just say this very quickly, okay, that if delta n is equal to 0, Kp is going to equal Kc, right? Because all of this, anything to the power of 0 is 1. So those are the only scenario, or that's the only scenario where Kp will equal to Kc, when the number of moles of gas on both sides of the equilibrium are identical. That's a question that's in the ACS study guide. Anyhow, talk about that more later. Who enjoyed today's class? I'd have to say today's class was the funnest class that I've had since we started this whole thing. I really enjoy talking about